So this video is going to be about other types of solids and their structures, and we're going to look particularly at ceramics. So ceramics, like alloys, have a long history in human civilization, and in fact the art of ceramics was perfected long before we really understood anything about the science. So what are ceramics? Well, ceramics are solids, inorganic compounds, so not nonmetals. We have metals and nonmetals in this mixture, or mixed and compounds or mixtures, that can be one or the other, that has been heated to transform it into a harder, more heat-resistant material. So, classic example, pottery from clay. So we're going to look at some of the different aspects of ceramics. So we're going to start with one of the basic ingredients, silica. So silica is one of the most abundant families of minerals in igneous rocks. Remember, igneous rocks are volcanic rocks. So silica has the empirical formula SiO2, but it turns out that silica structures can be quite variable. So they have many what we call polymorphs. Poly for many, morph meaning form. So they all have the same empirical formula but different crystal structures and different properties. So silica, SiO2, is a covalent network solid. So just like we saw with carbon, we have all the atoms bonded together. So the silica atoms are bonded each to 4 oxygen atoms, and those are connected to other silicon atoms, and so on and so on. This covalent network property. So some of those solids are crystalline, but some of them are non-crystalline, which means they don't have long-range order. So there's no unit cell that you then copy and repeat. The atoms are kind of in a disorganized state. We call those kind of, at least silica, we call those kind of materials glass. So silica is an important component of glass. You also find it in sand, and it's present in a lot of rocks and so forth, as already said. So here's an example of one of the famous polymorphs of silica. This is quartz. So crystalline quartz, it's a crystalline polymorph of silica. And so these little tetrahedra here represent the fundamental building block of quartz. So there's a silicon atom right here in the middle of this little pyramid shape, this tetrahedron, and there are oxygen atoms then on the 4 corners. Each of these oxygen atoms will in turn be connected to another silicon atom. So you see this oxygen right here is connected to this silicon over here. Each of these dashed lines then represents another connection to another silicon atom. So all of these little tetrahedras connect at their corners. You'll also notice that they form these little 6-membered rings. The tetrahedra have these little hexagon shapes. So there's kind of empty space in the middle, but the 6-sidedness, you can see, kind of propagates through to the overall structure of the crystal. It has kind of a 6-sidedness to it. Another polymorph of silica, on the other side being crystalline, this one is now amorphous, without form. This is obsidian, which is a kind of glassy form of silicon. So in this case, the silicon atoms are still have the SiO2 formula, but now the bonds are disrupted, so sometimes you're not connected to an oxygen atom or a silicon atom, and things are all jumbled. There's no organization in this case. So this is characteristic of glasses. Now we're going to look at another variation on this theme. We're going to look at silicates. So silicates are actually anions. So we have this anion form. Now we have to have cations to go along with these guys, and we'll talk about those in a minute. So silicates are ionic compounds, and this is an example of chrysotile, which is an ionic silicate. And it's made up of these units, Si2O5, 2- anions, and there can be many of these, so that's what the N means. There may be N of them, lots of them. So let's look at the structure. So you may say, hey, you just showed me this structure. But in fact, something has changed here. So again, we have the little tetrahedra with the silicon in the middle, connected to 4 oxygen atoms, covalently bonded to 4 oxygen atoms. But in this case, the little dashed lines connect to other silica, but you'll notice that some of the oxygen atoms are not connected to other silicon atoms. So these are single bonded oxygens. These single bonded oxygens then hold these extra electrons that are in this charged state. So they are not covalently bonded to another atom. So that's how we get our extra charge. So even though it looks similar, it's in fact a little bit different. And so without this extensive connectivity, these materials change their properties a little bit. So chrysotile is one of the principal forms of asbestos, and we know something about asbestos, that it's a good insulator, but it also flakes and fluffs and breaks off really easily. it's inhaled through your lungs, and it can cause lung cancer, so it's particularly damaging, perhaps. So now we're going to look at a particular kind of ionic silicate, the aluminosilicates. So we start off with the silicates. Here's one right there, silicate. And we're going to imagine that this oxygen is one of the ones that has the excess electrons. So what we can do with that oxygen is it can now ionically bond to an aluminum cation, Al3+. Now while I say ionic bond, in fact this bond right here is one of those in-between kind of bonds. It actually has significant covalent character, even though we still call this an ionic silicate. So what we end up with are these silicates bonded to the aluminums, and then the aluminums will bond to hydroxides. So these are hydroxide anions on the top here that also coordinate to these aluminums. So you form these little layers. So here's one layer that I'm kind of indicating right here. So hydroxide ions, aluminum ions, and silicate ions, they form a layer. Then you can have another layer underneath, and it will continue down here. And the layers are then held together by hydrogen bonds between this OH right there and this oxygen. So that little dashed line represents a hydrogen bond that holds these layers together. So we've got these layers that make up aluminosilicates. And water actually has a hard time, pretty strong affinity on the surface, but because of these strong hydrogen bonds, water has a hard time getting in to disrupt these bonds. So aluminosilicates then make up clays. So clays will wet fairly easily, you can shape them, and then as you begin to heat them, they will begin forming these ceramics. So we start out with this kaolinite, and we begin heating it. We'll drive off some of these hydroxides as water. Continued heating will break off some silicas, SiO2, so that we end up with a mixture of aluminas and silicas together in one compound. And once we've done that, we've formed the ceramic material. So this is one example of how you can go about forming ceramics from some other fundamental units. So there's a little bit about ceramics.